Assalamu alaikum everybody. This is me Khalil Al-Houthi. For today, inshallah, we'll show you how to solve the lab parts. This is the first lab. It's made up of two components, component 1 and component 2. First of all, I will show you how to solve component 1. So I shared with you some materials in the Moodle. You'll find them in week 3, the current week. First of all, this is the slides. We are right now in this chapter. We started it in last Sunday. I will continue, inshallah, on the same chapter next week. Apart from that, you'll find that there are other documents. First of all, these are some data. So if you open this one, you get the data. I will show you how to use them. Then scroll down. You'll find a simple software, a modeling software. We use it to model the gravity data. Those data are gravity data. We try to create some subsurface models. So this is what we call inverse modeling. We do have the data. From the data, we create models. And associated also with part one is what you need to submit. What are the deliverables? So if I open this, the same document, I already downloaded it. It's this one, lab 1, part 1. You will see what you need to submit, what you need to work on. I gave already some guidelines how to get the software, get the data. The data name has been changed. Instead of modeling, it's basically data. The software name is FastGraph. Fast is basically saying doing gravity modeling in a fast way. So your task is to create two bodies, two simple bodies. One of them is a spherical body, the other one is cylindrical body. And you need to change the parameters, the depth, the density, the radius of these. For the cylinder, you can even change the azimuth. And you try to manipulate them interactively until you'll find that there is a good match between what we call observed data and the calculated model or the calculated data from the model you created. So let's start. We'll show you how it works. Here is the software. I need to RR the software. I basically use a software that can RR zipped files. So I'm using the already default one that comes with Windows. So I just simply go right click and RR. Um, I have myself another software called WinZip. So if you're using Windows 7, sorry, Windows 11 right now, for Windows 11, scroll down deeper, you'll find that there are more options. Within more options, I use 7-zip. 7-zip is available online. You can download it and install it in your system, whether it's Windows or other operating systems. However, the software, this one, works only for Windows. The one I'm sharing with you, it works with Windows. So let's unroll it. I get a pop-up window, select destination. We save it as a new folder in the same destination, in the same directory. Extract. It won't take long. We see that there is a new folder. That's the one. I can delete this one if I like. Yeah, let's delete it because I don't want to consume space in my computer. Open it, go deeper. So this is the software. One thing you can do if you're in Windows to see the file extension. Sometimes Windows does not display the file extension by default, so you need to go to View, Show, and just tick this one, File Name Extension. If I open it, that's what you see. So let's create a profile first of all. This software is ideally used for 2D modeling. We can't do much of 3D modeling in here. We need more advanced softwares. So to create actually a profile, we simply click on this icon, add a cross section or a profile. So let's click on it. That's it. I can maximize it. So this is the thing icon I clicked, and I need to get data. So I don't have data right now. So I scroll here. There is no option of data. So let's get the data. How to install the data again? I go to the same module location and I simply, these are the data. You see, the first one are the data. I right click and save link as. So I save it. I won't save it again because I already have it. I don't create a duplicate of the same data. You just simply say click on save. It will be saved in the same destination. If it's not the same destination, you can change where to save it. So I have the data. Let's bring them. How I can bring them? I click the icon just below the profile here. Add observation set. These are observed data. So let's click and let's search in the same directory. I go, I believe, one step back, back. Here is the directory or the working directory. These are the data.txt. They are in text format. I double click or click and open. So it will ask you what are the units, what's the acceleration units. We'll study inshallah later on in the gravity chapter what are the conventional methods of unifying the gravity units. The most standard one is actually meter per second squared, whereas in geophysical surveying, the variation in gravity values, the difference in gravity, for example, from one point to another point, you're comparing two different points, you'll find that this value is very small, is actually very, very small. So we better use another unit than meter per second squared. The other minute, or other unit is actually milligal. So let's accept the defaults. And right now I'm able to choose it. You see, here is the one. What you see, two parts, the upper part, the y-axis is the gravity unit, milligal. So I have taken a measurement here, another measurement here, and so on. So these are the measurement points. And the y-axis represents the difference in gravity from one point to another point. The difference, not the absolute gravity, not 9 point something. It's the tiny value or the difference from one point to another point. So what we see that the density is increasing in here, and the density is the largest in this area. So I need to create two bodies. One of them is a sphere, the other one is a cylinder, and manipulate them in a way to get their response, the gravity response from these two bodies, and the response should match the observed field, the observed data. So let's see how we create bodies. It's very simple. You just go a bit down. You can add a sphere. The first icon is simply the possibility of adding a sphere. Let's click it and give it a simple name, sphere, and give it a density. So what are the density ranges usually? Pure water has a density of 1 gram per cc. Saline water slightly has a higher density. Density, for example, of a limestone is 2.7. A good limestone, pure limestone is 2.7. It varies slightly because of different contents, lithifications, mineral contents, density of the rocks, and so on. However, the average value of, for example, limestone is 2.7 gram per cc. However, gram per cc is not an SI unit. The SI unit is what? Kilogram per meter cubed. So gram per cc, cc means centimeter cubed. So if I need to convert from gram per cc to kilogram, I need to multiply by 1000. Multiply by 1000. Here is the unit. You see, kilogram per meter cubed. And this is actually the real density of the material. It's not the contrast in density, the difference in density. So let's give the sphere a value of, let's say, 500, 5500. And let's give it a radius of 10. So you see, a body has been created. When I drag it somewhere, and that's the blue curve is the response. This is the density variation. If we have a sphere of density 5.5 gram per cc, what's the density of the surrounding is 0. So if I have a body of this specific density and with these parameters, how deep is it, what's its radius, that's what I observe. So if I decrease the radius, you see how the response changes, the gravity response, it decreases as well, the blue curve. So I can move it wherever I like. And yeah, I almost match one parts. So let's create also what I call a cylinder. Cylinder, you can name it whatever you like. So let's name it cylinder 01. Let's give it a 3300 and I give it a radius of 5. 5 radius. And let's give it, for example, an azimuth of 60 or minus 60. Let's make it minus 60. So your task in here is to change the parameters until you'll find that there is a match between the two. What you can change the radius, you can change the depth of either bodies, or you can change as well what we call the density, the most important parameters. So where I can find those parameters, if you double click again on the name of the body, these are the parameters. So how deep is it? It's 22 meters below the subsurface. What's the radius? That's the radius. What's the X location? This is 0 and it's 74 meters from the start. And what's the density? This is the density of this sphere. And you can play around. You can play around with them. It's your task to let them match. So you need to modify either of these until they match. Until the observed field matches. Not exactly, you won't be able to exactly match the two. The reason being we know that the subsurface is very complex, is highly heterogeneous, and we are just simply simplifying it. In reality, there are no bodies there are not no ore bodies those which are perfectly spheres or cylinders. But as I said, the objective is to simplify the modeling process. Otherwise, we can't make such simple softwares. Uh, to make modeling for more heterogeneous bodies or irregular bodies, we probably need a better or more advanced softwares. This can do simple modeling, 2D modeling. So it's your task. I gave the same session uh, yesterday, and there were some students who did a really great job. Uh, they they changed the parameters of the body until the two matched. These two cores, one of them, the black one, is the observed field, whereas the blue one is actually the calculated response, the gravity value because of having two bodies. Each body has specific parameters. I'm talking about parameters which are what? Density, how deep the body is, the depth, and the radius. So what you need to submit, I go back here. First of all, you need to take screenshots of your modeling results. I usually use this software called Snipping Tool. If you search for Snipping Tool, it comes by default in Windows, Snipping Tool. So you click New and just take a screenshots. That's what you get. Copy it and paste it here. The next thing is to find those parameters. So what's the density of the cylinder? From where you get them? Again, cylinder, double click, that's the density. This is the azimuth. Azimuth is not required, but the depth is required. Z value is required. Minus in here indicates that it's below the subsurface. And we have the radius as well. So you can play around with these parameters, 1, 2, 3, until you'll find that there is a match between the two. And for the sphere, again, you can get those parameters once you double click on the name of the body. The name can be anything you specify, not necessarily sphere or cylinder. They are arbitrary names. Let's go to the next question. What's the next question? So explain the difference between forward and inverse modeling in geophysical data analysis or modeling. So what's the difference between the two? It's something we already explained, I believe. What's the difference between theoretical and observed data? So theoretical data are actually the response of the model we create, whereas the observed are the actual data we collected from the field. You can expand on my answer, make it more clear, but this is the simple answer I can give. How often? The question here it states, the question number 5, is it easy that you create a subsurface model that gives you a response exactly matching the reality, the observed field data? And are these two exactly possible, exactly can match each other? That's the question. Is it easy? Is it plausible? Is it possible? How likely is it? So this is the question you try to answer. Definitely it's not easy. Uh, it's challenging. You can't make it very close or exactly close. Your task is, or objective is, to make them close to each other with a percentage, with an error in percentage. The error percentage, if it's 3%, 5%, it's fine. Whereas if the error percentage is, let's say, 100% or 200%, then you are totally doing something wrong. So finally, this is the question. I already answered this question. So the question states how you can justify that the model you created is a good model. It's plausible. It's representing the geology. There are two things. Two things we can use as benchmarks to validate the models we created. One of them is how closely the calculated field matches the reality, the observed field. What is the match between the two? That's one thing. The other parameters is is the model you created geologically plausible, possible, can be, can the can the subsurface has such bodies or not? That's what I mean by plausible. يعني مثلا if I drag this one, bring it to the surface, what do you think? In reality, would you see something? Is it possible to have something like that geologically or not? So someone might ask, then is a sphere is possible? Yes, A sphere usually represents cavities in the subsurface or salt domes. They are not perfectly sphere, but we are trying to simplify them. What about cylinders? Cylinders represent what? Tunnels in the subsurface, dikes, for example, and so on. So those are plausible geological bodies, but we are trying to simplify them, removing the irregularity, complexity in the subsurface to make the process of modeling much easier. So this is part one. Let's move to part two. I don't want to make this video very long. So I close everything with part one. That's the software. This is the deliverables you need to submit. Don't save. We close the software too. Okay, so here where you submit the part one, let's go to part two. Part two have um, two materials available in Moodle. One of them is some simple slides. I'm trying to explain what is gravity modeling, how we usually do gravity modeling. In here, instead of inverse modeling, the first part, we are doing actually forward modeling. What we are doing is that there are a body, parameters of the body we know, and from those parameters we try to create the response. We try to create the data based on the parameters or the model parameters. What's the thickness, density, and so on. So there is a slides, some slides explaining what's gravity modeling. So let me explain briefly what's gravity modeling. So gravity field is dependent on actually Newton's law. And Newton's law, G is basically force. It's mg, which is supposed to be m, start writing. It's mg. This is equal to force. And also force is equal to, gravity force is equal to g m over r squared. So what you see, little m will cancel with little m. And gravity value, acceleration to gravity will equal to what? That's the gravity potential, the force of gravity. Whereas this one is the acceleration to gravity. So it depended only on the mass of the Earth, total mass of the Earth, the gravity constant, which is this parameter, divided by the radius of the Earth squared. So if we know, let's assume that we know what's the gravity value, we know the acceleration to do our average value of acceleration to due to gravity, that's the value. We know what's the radius of the Earth. We assume that we know it. Right now we know it by um, very precisely because of satellite data and so on. We can calculate or estimate what is the mass of the Earth, the mass, the total mass of the Earth. And it's a very large number, you see, megagram. And if we could convert it to kilogram, this is the value. And if we know what's the volume of the Earth, that's the mass, we can calculate what's the density of the Earth. The density of the Earth is some value around 5.5 megagram per meter cubed. It's very large number. It's actually very large number, whereas the average value of the average density of the crust is way smaller. It's 2.7, 2.5. Why is that? Because 2.7, 2.5 gram per cc. So I need to multiply it by 1000 to convert it to kilogram per meter cube. Uh, why is that? Because there are some bodies, materials in the subsurface of the Earth, which are of very, very high density, like the iron is 7,800 kilogram per meter cube, 7.5 megagram per kilometer cubed. So if we convert it to kilogram, it becomes 7,800. So having this knowledge, how I can calculate the density, how we can calculate the gravity, the acceleration to gravity, delta G, and assuming that I know what is the density, not necessarily absolute density. In geophysical surveying, specifically gravity surveying, we are not of interest to the absolute gravity or absolute densities. We are measuring relative change, the change in acceleration due to gravity from one point to another point, the change in g from one specific point to another points. Those points are the measurement points. I take a measurement in a specific point, I move by some distance to another point and measure how much gravity has changed. So if I'm interested in changing gravity, uh, the values of density are represented by change in densities, not absolute densities. So here, for example, what you see, a body is a sphere and it at depth of 100 meter, it has a radius of 50 meters, and the change in density is the difference in density between the body and the surrounding is how much? Is 0.3 megagram per meter cubed. Megagram per meter cubed. So this is the difference in density. And what it means? It means that this body having some higher density than the surrounding by how much higher? This specific value. So having these numbers, can I calculate delta G? Can I calculate if I measure at point C, how I can calculate uh, the density, the acceleration to gravity based on change, this specific change in density. We can use the same equation, the gravity equation, since we are measuring change in density, not, not the absolute masses, change in masses. We say delta M. We use delta M instead of the absolute mass. And you know that mass is equal to volume times density. We need to know what's the volume of the sphere and the density difference. The density difference is given to us. That's the density difference. So plug in these values back to the same equation. We have the G, constant of gravity. This is that's the what we call center of the Earth radius or depth in this case. In this case, because I'm not concerned about the absolute values, I'm concerned about what I call the difference in gravity from one point to another point. So radius to the center of the Earth is converted to how deep is the body. Because everywhere the gravity is the same. Yani, elsewhere, in all places, the gravity is the same. So radius will be converted to depth of the body. The other parameters are what we have 4 over 3 pi r cubed. That's the volume. This is the volume, and that's the difference in density. We plug in the numbers we already know from the previous slides. These are the numbers. We have constant of gravity, the depth of the body, what's the radius, and the difference in density. That's the value we get. So it's 1.048 times 10 raised to power minus 6. It's a very small number. يعني the average value is 9.8 meter per second. squared. So you see how small this number is. So if those changes are small, it's representing the change in this specific point at point C. Uh, so we instead use a different unit. The other unit is milligal. It's called gal or milligal. So 1 gal is equal to 0.01 meter per second squared. There is also another unit called gravity unit. Gravity unit 1 milligal equal to 10 gravity units. And 1 milligal is equal to 1 times 10 raised to power minus 5 meter per second squared. Those are just simply some conversions. Um, so what about measurement of gravity at some other points, not necessarily at the apex or the top of the body? We know how we calculated it. That's very simple. But if we are measuring somehow not at the apex of the body, the calculation is not that simple. In gravity, we are always measuring the vertical component. We are not measuring the horizontal component. We are measuring exactly the vertical component. And this is something we'll discuss later in the gravity chapter, why gravity tools or equipments measures only the vertical components because they are dependent on a spring system. However, I don't go to the details because again, we'll discuss it later on. So it has some force, that's the force, and the force is represented by length. Any force can be represented by length and direction also. So the length does not change. The direction might change. So here the direction is the same, length, but it's pointing to the center of the body. And what I'm measuring? I'm measuring the vertical component, that component. So I'm measuring actually the vertical component. What happens? You will find that this vertical length changes because it's tilting. If I go again farther away, this becomes smaller, whereas this length is equal to the previous length, is equal to this length as well. So these, and these are equal, but the vertical component is higher. The vertical component is higher if I'm measuring exactly at the top of the body. While I'm only measuring the vertical components, not the horizontal component, that's the horizontal components. I cannot measure uh, very easily the horizontal component of gravity. So you see its values decreases. And how we can quantify it? We can quantify it. How we know that what's the length of this one? What's the length of the vertical component? It can simply be calculated if we already know the what I call hypotenuse, الوتر. So, and I need to know what's the angle. So the angle is need to be known, and that's the hypotenuse because cos theta equal uh, adjacent المقابل على الوتر. Adjacent is this one, the red one, الوتر. So hypotenuse, sorry, opposite or adjacent, sorry, adjacent over hypotenuse. So how I can know this one? Just multiply these two. I'm multiplying this one with this one. This is a force. Force can be represented, as I said, by a length. So again, the same configuration. What's cos theta? Is, as I said, Z which is the adjacent المجاور على الوتر. الوتر is the R. And from Pythagorean theorem, we know that R square is equal to X square plus Z square. This is how we can know what's the R. And this is the state we are right now. This is exactly equal to here. So if in this specific case, cos is 0. Cos 0 becomes 1. Cos 0 becomes 1. So there is no change. So let's do some changes. So let's replace cos theta with the value we know, z over r. So it becomes z divided, instead of r square, it becomes r cubed. And let's also substitute r with the parameters we know. It's the distance from the center on the surface and how deep is the body. This is what we have, and we substitute it. We substitute all in here. It becomes these parameters. And you know that we are measuring change in density, and the change on density represented to change in volume we are measuring. Change in volume represented by change in density. And we need to know the volume then. Volume multiplied by change in density gives you change in volume. So this is the final equation we can use to calculate the acceleration due to gravity of a sphere. That's the equation we need to use. So let's see how we can solve part 2 based on the knowledge we just gained. So in here it's saying that we have a body. It's Z is 50, and density, or I call it P rho, is equal to 2 gram per cc. It becomes 2000 kilogram per meter cubed. And it's at the distance of x is equal 100. It's how far is it? The center point is 100. And how deep is it? Uh, mm, Sorry, what's the radius? I forgot to write the radius. Radius of the body is sphere. The radius is 10 meters. So let's do modeling based on the equation we know, and we simply use Excel for modeling. Uh, so let's use Excel. Here I have distance. This is the parameter that changes. This is the distance. So I start, as I said, it's at 100. The center, the body, is at what 100. So how I can represent it? Let's make some conversion. Let's assume that this is 0 and here is minus 10, minus 100. On the other side I have 100. So the body is in the center. This is how we model it. So let's create some data. Those are measurement points. And the body, I do have a body in the subsurface. I'm taking measurements on many points on the surface along a line. And the line is crossing the body at the center. So let's make 200. Then it's supposed to be minus 200 and 199. And let's keep dragging. You see it decrements automatically, and I'm right now at 100. The next side gonna be 200. So those are the x values. I go back to the equation. So that's the x. The x is the only variable here. Those are noun values. The radius is noun. G is the constant. Z is known. Density variation is known. Those are given to you already. And the other one here is delta G. We need to calculate what's the delta G. We need to calculate basically this value. So how we do it? We say here I have the depth. Here I have the radius, and the density, and constant G. What's the value of the constant G? Let's bring it. That's the constant G. Let me copy it. It's already in SI units, so meter cubed, and we just take this value and we use it. There is one conversion. So here it's supposed to be in kilogram. Right now it's not in kilogram, so we need to convert here. We bring it to kilogram. We divide again by how much? We divide by 1000. We divide by 1000. So this is becomes this. Oops, sorry. Let's make it a bit smaller. And I simply add E minus 11. This is the value. Becomes E minus 11 in SI units. Here it wasn't SI units. Meter is SI, second is SI units, but megagram is not an SI units. Kilogram is the SI units. What about the other parameters? Let's use them. That is 50 meters, 50, and radius is 10, and density is 2000 kilogram per meter cubed. Those are the parameters. And let's create our equation. Let's create our equation. And bring this one here, the PowerPoint, so side by side. And I will show you how you can use the equation. So here is it. I create an equation, open brackets, and the first parameter is basically the G, that's the value. So there is one thing I need to emphasize before we move forward. Let's say that I have a number here, 200, and this one is equal to this value. So what happens if I drag it down? It changes. You see, it takes the next point. How I can make it constant? How I can make it so when I drag, the value won't change? You can simply add a dollar sign between the letter, in this case is A, and the number, a dollar sign. So right now, if I drag again, you see it won't change. What about if I drag it to the right? It changes. It takes the next value. What I shall do to make it a constant, you can add also again a dollar sign before the letter. Before the letter, add a dollar sign. So if I right now drag again, it gets me or give me the same value again and again. So we need to use this parameter. So here as the value, if I drag If I drag elsewhere here, I'm using it here, so it's equals, um, I open a square brackets and use this one. I need to make it constant. How I can make it constant? Just add $sign again here as well as here. Before the letter and after the letter, in between the letter and the number. And I multiply it by what? Let's see the equation. I multiply it by 4 over 3 times what? Times pi. So I can get pi. Pi is simply pi, and that's the pi. Pi, write pi y, py, and in between curly brackets. Opening curly brackets and closing curly brackets. Then multiplied by r, radius. Here is the radius. So I just click on it, radius. However, I need to ensure that it won't change when I drag. This is raised to power, this is raised to power 3, os 3. And then change in density, multiply by times change in density. That's the density value. And finally multiplied by z. Uh, what mistake I made? Multiplied by, yeah, here, O 4. I thought that's 0, not O. Yeah, this is true. It's basically O 4. And finally I multiply by the z. And let's close the curly brackets. And we divide by x squared plus z squared, and the whole is raised to power 3 over 2. So let's create the denominator. It's called, we use, we basically use the power. Power is a function. It's a function in Excel. The first parameter is the value. In this case, this is the one. The other parameter is the power. The power is 3.2. It's equal to x. So where is x? X, hey, that's the x. So divide by our uh, x raised to power 2 plus uh, z. Where is z? That is depth raised to power 2, and the next part is the power itself, which is 3 over 2. And let's close it. Let's close it. What happens? I'm supposed to get a nice number. That's the number I get. So what shall I do? I just double click. It will continue itself. Oh, I forgot something. So those should here all supposed to be not changing. I forgot. Yeah, this should not change. Uh, uh, the depth should not change as well. Here also, the depth should not change. M5 does not change. The only thing that change is A. I was getting all zeros. What's still changing? Yeah, I forgot. Still changing. Didn't I update it? I thought I updated it. Okay, this should be updated too, and here it should be updated too. Yeah, that's correct. Perfect. So it's working. Let's maximize it. So this is the thing you need to do. You need to create an equation and simulate. Let's plot it. How we plot it? We drag and highlight these two columns, starting from column A, then column B, go to insert, then go to here charts, insert chart, use this scatter plot, scatter XY, and choose this one. This is the data you get. That's the data you get. Interesting. And if I go back right now to the deliverables, you need to copy paste this one. You need to copy paste the the image you have created. Again, we use the same tool, snipping tool. Let me open it again. Copy. You can, if you want, you can uh, give a label X label, Y label, X label. In this case is the distance. The Y label is the acceleration. Someone was calling me. I just hung out. So you need to copy this one, bring it back, and paste it here. The last question is, what happens if I change these parameters? What happens if I basically change these parameters? What do you think happens? This is a constant. This won't change, never ever. That's the gravitational constant. The other parameters might change. The depth might change. The radius might change. So let's see what happens if they change. A simple way, I'm not sure you are aware of that. A simple way is to create controls. So how I can create controls in Excel, you can go to developer, this developer tool, and you can add a control. Let's add a scroll bar. So I'm adding a scroll bar. I'm adding a scroll bar. So when someone was knocking my door, let's say this is the scroll bar for the depth. And let's format control. Let's say the current value is 50 and the minimum value is let's say 10, maximum value is 200, and we go by an increment of 5, 200. And when I change it, drag it, it changes by, let's make it by the 1. And it represents this cell. So that's how is it, you see. If I drag right now, you see what happens. That's the depth. So it changes everything. The values there change too. The values in here, everything changes. Let's do something. Your task is to answer what happens if I increase or decrease the depth. The minimum value is at 10, the maximum value. You can make it some other values, but that's how it change. You can just simply drag it. The maximum value is at 200. Let's create another one for the radius. That's the radius. slightly shorter. And let me, current value is 10, minimum value is, let's make it 1, maximum value of, let's make it 100, fine, and it represents this cell. This is the cell it controls. Let's change it. Oops. See what happens. I change the radius. Let's do the same for density. Again, control. I'm adding a scroll control. Bring it here. Right click, format control. The current value is 2000. Minimum value, let's say 50. Maximum value, let's say 6000. And here, since this is very large range, we make the increment, let's say 50, and it represent this value. See, if I change, what happens? The task is to document, to write down what happens to the curve, to the data, to the delta G when I change these three parameters. Great. And you write here for the depth, what changes or how the response change when you change the depth. Again, what changes if you change the density, and finally, what change, how the curve change if you change the radius of the body. So by that, I conclude um, the records. It might have taken 1 hour since I started. So I will upload it soon, inshallah, and you get it in Moodle as a link in video, in YouTube, sorry. Goodbye.